Hello, in this modern OpenGL video, we're going to be looking at projections and coordinate systems. First of all, I just want to get a few things out of the way. Even though I'm doing this on a Mac, using GLFW, using the Xcode IDE, it doesn't matter because this tutorial is an OpenGL tutorial, and if you do it on Windows using Visual Studio and you've got it all set up, and so you use SDL or SML or some other framework for rendering a window, that's fine. This code will still apply. I've had quite a few questions regarding that, and the code is universal, so I just wanted to get that out of the way. These videos, and this video in particular, is based on the work of learnopengl.com and open.gl. There'll be links in the descriptions there. Feel free to check them out, and they do explain the concepts that we cover in this video and in these videos in a lot more depth. So the first thing what we're going to do is cover coordinate systems. There's two types of coordinate systems, a left-handed and a right-handed coordinate system. Best way to visualize it is to put up both of your hands, so your index fingers are pointing up like so. Your middle fingers are pointing towards you, so you want them pointing towards you, not in at each other, and your thumbs are pointing left and right. So your left thumb, the thumb on your left hand is pointing to the left, and the thumb on the right hand is pointing to the right. Once you've done that, the direction that your fingers and your thumbs are pointing are the positive direction for that axis. So going up, the way the index finger is pointed is positive for Y, this is positive for Z, and the opposite way will be negative for Z and positive for X. So you should be able to see the difference between the left-handed and the right-handed is the X if we have it in this particular sort of positioning. Positive value for X is right in the right-handed coordinate system and is left in the left-handed coordinate system. OpenGL uses the right-handed coordinate system and Vertex uses the left-handed coordinate system. So that's quite a bit to take in. Feel free to ask any questions that you may have on our education platform, sonarlearning.co.uk. There'll be a link in the description to that. Plus there'll be a link to this picture if you want to check it out again. Also, there will be links to learnopengl.com and open.gl which cover this in more depth. So now that we got that out of the way, there's two different types of projection. There's perspective projection and orthographic projection. Perspective projection takes into consideration depth, which generally speaking in pretty much every game you would. Whereas orthographic projection doesn't take into consideration depth. So objects or part of an object that is further away from you still looks the same size. So if you had two identical objects and one was further away, it will still look the same size. Whereas in perspective projection, just like real life, it would look smaller. You might be thinking, where would orthographic projection ever be useful? One example is in architecture, when you're creating and laying out designs and you want to have sort of objects behind other objects, but because you're doing measurements, you don't want them to be smaller, you still want them to be essentially the same sort of size. So that's the two projection types. So let's actually start coding it up. First thing that we want to do is go to our Vertex Shader. We need to remove the color value because we are just using textures now and we're not really using colors anymore. So we can just get rid of these. You can easily add them again if you need them, but we don't. So we're going to just delete them and delete this our color equals color from here like so. We are also going to delete, I'm going to delete the transform as well. Delete this transform because we're going to have a few different ways of transforming sort of our world, but you can add this specific transformation back in at a later date if you want to. In here, there's a few things that we need to add. We need to create a uniform 4x4 matrix, which is going to be the model matrix. Then we need a uniform 4x4 matrix, which is the view matrix. Let me zoom in so you can see it a little better. Then we need a uniform 4x4 matrix and called projection. So this is the projection matrix, and the three different types of matrices do very important stuff. The model matrix converts local object coordinates to camera coordinates. The projection matrix converts those camera coordinates to normalized coordinates, so coordinates between 0 and 1, and the view matrix converts the normalized coordinates to window coordinates, aka what your screen is, or what your sort of window is. So now that we've got all of that done, to implement it, we would just put model times view times, sorry, we need to do projection. It doesn't really matter what order we have them in. Actually, I believe it does. Sorry, my bad. I believe it does. Model times vector 4. So yeah, now that we've done that, if we go to our core fragment shader, and in here there's just a couple of things that we need to do. We need to get rid of this our color vector 3, leave this color value because that is just the texture itself. What we want to do is go to the main.cpp. First of all, we want to get rid of the EBO. We're not using the element buffer object anymore, so let's get rid of that. Get rid of any other instance of element buffer object. Get rid of the color attribute. We're not using that anymore, and get rid of the EBO from here. So now that we've sort of cleansed our project, we are going to enable depth. And the reason we need to enable it is because if we've got 3D objects or objects that are further away from you or nearer to you, you need to account for depth. So if we go to anywhere around about here, we're going to put GL enable, should be a capital E. This is GL underscore depth underscore test, and if you scroll down, you also need to clear the depth buffer. So you just put vertical bar, put GL underscore depth, GL underscore depth. Zoom in a bit. Underscore buffer bit. So now that we've implemented depth into our application, we're going to actually get rid of the indices and the vertices. I've got the indices and vertices, the vertices right here. We're not using any indices for this video because there's quite a bit here. I'll briefly touch over what it's doing, and we'll be switching between the two of them to illustrate orthographic projection and perspective projection. So each one of these correlate to a particular face. So this will be phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6, because we're going to be doing a cube now. We're actually going to be rendering a 3D object to help illustrate perspective and orthographic projection. So this is sort of a projections, coordinate systems, and drawing a cube video tutorial. The first three values on a row is the X, Y, and Z, and the next two are the normalized texture coordinates. So we just got 0, 0, 1, 0. Very simple stuff. We've covered pretty much all of this before. What I would actually recommend you do is look at each one of these sets and try and figure out which face on a cube they correlate to. And especially once we've actually got it rendering and drawing, you can sort of say, oh, it correlates to this particular face. That would be really awesome to help you learn. So now once you've done that, all of this code is pretty much okay, bar a couple of things here. This needs to be times by 5 because there's 5 different pieces of information on each particular row. The size of GL float is fine, GL void is fine. We also need to change ×5 for the texture coordinate attribute, and apart from that, we also need to bump this down to 3 because we've changed the vertices up slightly. In terms of our texture loading, we shouldn't have to touch any of that code whatsoever. So after we've binded the texture, or unbinded it essentially, and cleaned it up, what we're going to do is do glm : actually, yeah, glm : and we're going to do mat4, which is a 4x4 matrix. I'm going to call it projection. So this is going to be our projection type. First one I'm going to show you is perspective projection, because that's the one that you'll probably be using most of the time. I'm going to put projection equals glm : perspective, and the perspective takes a few values. First value is the field of view. I'm going to put 45 degrees. This is a very common value for video games. If you have a higher value, it's essentially the angle between the bottom and the top. I'll actually show you an image on Google in a moment of a view frustum, so you can see each one of these particular pieces of information in play and how essentially the camera system works. So the aspect ratio, you would just get that by doing screen width divided by screen height. This keeps it dynamic, and we're going to cast this to GL float, and for the near clipping plane, if you want to put 0.1 f. For the far clipping plane, I'm going to put 1000.0 f, and we'll explain what each one of these means with a simple image. So we're going to put view frustum images. So this is what a view frustum is. We're going to try and get one that has the field of view in it as well, so we can just explain all of it at once. So here we go. This is what we've got. So this will be sort of like as it says here, the center of projection, where our virtual camera is. We don't actually have like a physical camera there. Sometimes they actually, diagrams will use sort of like a camera, as you can see, and here and there, just to illustrate what it technically is, but there isn't a physical camera in your game. So if we go back to here, this is the near clipping plane, which is this 0.1 f value, forgot the semicolon. This 1000.0 f refers to the far clipping plane, and what this means is anything nearer than the near clipping plane won't be drawn to you on the screen, and anything further than the far clipping plane, so anything like outside of here, won't be drawn to you either, and anything outside of this view frustum, outside of this box, won't be drawn to you either. The aspect ratio is the width divided by the height, and the field of view is basically how tall it is. Some games like Doom have a large field, like the original Doom have a large field of view, so you essentially get more of a square boxy style of game perspective. Here's another cool image. This refers to a perspective projection, and this refers to an orthographic projection, where there isn't an angle and there isn't sort of, as you can see, an increase in the height and the sort of an increase in general in between the coordinates compared to there is compared to the orthographic projection. In the orthographic, everything looks the same size regardless of distance. So that's the view frustum covered, because that's essentially what this is creating right here. And now that we've created the projection matrix, what we can actually do is start creating the model and the view matrices, and you want to do that actually within our while loop. So if we go to anywhere down here, we want to, what do we want to do? Actually, I think we could probably, yeah, we're going to get rid of, how much code do we need to get rid of? I'm just trying to think. We're going to get rid of the transformation. We're no longer using that. Remember, you can easily pass it back in. That's not a problem at all. And I would recommend, as an extra task, once you've done this, you got it working, implement a simple transformation for just that particular model and get it implemented in the Vertex Shader. I'm going to get rid of this particular code as well, like so. So we got the GL active texture. That's all good. What we're going to do, yeah, I'm just going to reorder this slightly. So I'm just going to cut that and put it before we use our shader. Get rid of that because we're no longer drawing a triangle. So now after this, we're going to, like I said, create the model and view matrices. I'm going to do GLM, let me zoom in. GLM, colon, 4x4 matrix, so mat4 model, GLM, colon, mat4 view matrix, and now for the model, it's going to be model equals GLM, colon, we're just going to put some initial sort of rotation in there, rotate, and you'll see why. And for the rotate, we're going to put model. So this refers to the matrix, the model matrix. We're going to put angle, how much we want to rotate it by. This is the part where you do technically need some SDL, SFML, or GLFW specific code. I'm going to be using GLFW code. It's not very hard to get some GL, to get some SDL or SFML code. I'm just going to be getting the time because I'm rotating. We've already covered this in a previous video where I provided links for SFML, SDL, and GLFW, so you could check them out, and those links will be in the description for this video as well. So just going to do GLFW get time, just getting the time between starting GLFW and now. So this is obviously only going to be constantly increasing, hence why we can use this as a nice way of rotating. Float. And what we're going to do, let's do times 1.0f. Obviously this doesn't change it, but this is a great way of increasing and decreasing the speed. You just vary this value. The next parameter that we're going to provide is GLM, vec3. And for this, in the x-axis, we're going to put 0.5f, 1.0f in the y-axis, and for the z-axis, we're not going to do any rotation. This is going to create a nice effect to our cool, really cool cube. Next, we're going to be creating our view matrix. So we're going to put view equals GLM, translate. So we're going to just move the view slightly. First of all, we specify our view matrix, which is view. Then we specify what sort of movement we want. Put GLM, vec3. And we're going to put 0.0f, 0.0f, negative 3.0f in the z-axis. So we're going to be moving it, the camera essentially, so we can actually see what is going on. Otherwise, we'd essentially be within our cube. So now that we've got that sorted, you might just be briefly wondering why we are adding a rotation and translation matrix. Again, this is just for this particular video. You may not want to add a rotation or a translation matrix. One thing to bear in mind is if you assign multiple matrices, so if you were to do this and there was one translation, one scale, you wouldn't overwrite the matrix already in model. It would just add another one, So that's something to bear in mind. So that is a great way of chaining up multiple matrices. Recommend that as an extra task as well. Try and chain up multiple sort of rotation, scaling, that sort of transformations. So now we're going to get the uniform location. If I just zoom in, I'm going to do GL int model location equals GL get uniform location. Where is it? Get uniform. I can't find it. I'm just going to type it out. Location. And in here, we simply put our shader dot program, very similar to what we've done up here. And the one that we are trying to get is, I think you've probably guessed it, model. We're going to duplicate these lines now. Change model location to view location. Change the final one to projection location. Change this to view. Change this to projection. And now we can actually pass these to the shader. So we're going to do GL uniform matrix for FV, because it's 4 float values. That's the reason we're choosing this particular method. You would just adapt it for any other sort of set of values that you have. First of all, we're going to put model location, and then we're going to put a 1 GL underscore false, and then we just put a value pointer to our model, so GLM : value pointer, and in here you simply put model, which is the 4x4 matrix that you created before. If you just duplicate this twice, zoom in, and we're going to change this to view, change this to view, change this to projection location, and change this to projection. So projection. Now let's zoom out. We also need to draw, zoom back in again, always zooming in and out in these videos. We need to actually draw our object now. So we're going to do GL bind vertex array, the vertex array object, GL draw arrays, and for GL underscore triangles, and for the first vertex we're going to start at 0. For the count it's 36, because, well, it's 36 because there's 2 triangles per face, and each triangle has 3 coordinates. Each 2 triangles makes it 6 coordinates. 6 times 6 is 36. You could use a very sort of draw element system that we used in the previous video. I recommend checking that out and trying to convert this one to the previous method of drawing as well. All good things for learning. We're going to unbind this, so we're going to GL bind vertex array, and we're going to put 0. Let's have a look. I honestly think we're ready to start running it now. So let's run it, see what happens, see if we get any errors. No error, that's good. Okay, almost there. It's probably best if we change the image from an image with alpha to an image with, well, no alpha. I've already got one here, luckily enough. But it looks like it's actually working, which is very good, first time. So let me just minimize that. So we now have our cube, and it's a pretty cool ass cube. At the moment, we just got the same texture applied to every single face. We'll cover that in a later video of how to use different textures. So now I want to demonstrate how to do an orthographic projection and the difference between an orthographic projection. So what we're going to do is uncomment out. Actually, I don't think I needed that other particular matrix. I don't think I did. No, I'll keep it. So I'm going to uncomment this out. Reason we're using a slightly different one will become evident very soon, because the way the orthographic projection works, it doesn't quite use sort of screen width and screen height coordinates. So we're just adjusting our values for this. I'm just timesing it by 500, but that will become a lot clearer. First of all, let's just comment out the perspective projection and zoom in as usual. Then do projection equals GLM ortho, and for the ortho projection, for the left value, I'm going to start at 0.0f. You can start at negative 47.8 if you want to. Best if you start at somewhere like 0.0f. Far right, and we're going to put GL float. This is going to take this. I'm going to put the screen width in here. You can put a smaller value if you wanted to. Bottom, same again, 0.0f. We're going to put GL float screen height. And I'm going to put near and far clipping planes, same system as before. So 1000.0f. You might be wondering, where's the field of view and the ratio? You don't need to do that, because it's more like this particular box instead of this particular one. So let's get back to it. It's moaning about something. No matching function called to ortho. Okay, GLM ortho. Let's make sure everything's all correct. GL float screen width 0.0f. GL float screen height 0.1f. Sorry. Yep, that's removed the error now. So the only other two things I want to change are the model and the view matrices, simply because it'll help demonstrate what we're trying to show. So we're going to do model equals rotate. Forgot about GLM : and we're going to put model 0.5f for the rotation, GLM : vec 3, and for these values we're going to put 1.0f, 0.0f, and 0.0f. So we're just rotating in the x-axis, just one axis to keep it simple. We're going to do view equals GLM : translate, provide the view matrix, and for the vector 3, put vec 3 we're going to move it by 0. Not 0. We're going to move it because it's actually going to start in the bottom left initially. We want to move it to the center, so we're going to do screen width divided by 2, screen height divided by 2, and we're going to put negative 700.0f. Otherwise, I've experimented with these values before. If you don't put this particular value for the cube that we've got set up, you won't be able to see the entirety of it. So just bear with me a second. Let's run this now and see what our cube looks like. So we've got our cube. It might look a bit weird. It might just look like a big long rectangle, but what's actually happening is this section here is the front face and this section here is the top face. We've rotated it, but without perspective it's hard to tell which face is which. But watch what happens when I comment out the view. Let's get back our old view. Let's bring in the perspective projection and let's uncomment out the other array. Now if we run it with the perspective projection, you'll see the key difference between orthographic and perspective. Looking at this now, it blatantly looks more like a cube. Obviously we can't see the sides or the bottom or the back faces, but based on what we're seeing here, it looks like a cube compared to how it did before. So this has been a video covering projections, coordinate systems, and drawing a cube. It is a lot of topics and concepts to take in, but don't worry, just practice them. Let's do extra tasks, compare orthographic and perspective projection, mess around with the values. Check out learnopengl.com, open.gl, which these videos are based on. There'll be links in the description, and you'll be a OpenGL ninja in no time. Also, feel free to post any questions you may have on our education platform, sonarlearning.co.uk. If you're stuck and you just want to check out the code, you can check it out on our GitHub page. There'll be a link in the description. And as usual, thank you for watching, and I hope you have a great day.